Good morning. The title of this video is Symmetry Operations as Members of a Mathematical Group. Having understood how to get binary combinations of operations in a few cases, it is an appropriate time to introduce the concept of mathematical group. The word group is actually a mathematical concept. It is simply a collection of entities or items which are interrelated, obeying four rules. These rules are: 1. Closure property. 2. Identity property. 3. Inverse property. And 4th, associative property. A collection of entities which are interrelated, obeying these four rules: closure, identity, inverse, and associative properties. First, let me give an example of an abstract group. The set of integers, for example, set of whole numbers, positive and negative, including 0. By the way, every group is characterized by a law of combination. The collection of integers, positive and negative, including 0, will form a group under the law of combination of addition. What do you mean by the closure property? If you add any two integers, the result is one or another integer of the set you have already considered. Any binary combination yields a result which is already present in the set. No result outside the collection of entities we have considered will appear. That is known as closure property. Then identity is property. This group should have a particular member. Members of group are usually called elements. Particular element, here it is additional, is the law of combination, and the identity element is 0. You can add 0 to any integer and that integer is left unchanged. So identity is an element which will combine with any other element, leaving it unchanged. 0 is like that in this particular abstract group. And what is inverse property? If X is a member of the group, it will have an inverse generally denoted as X to the power minus 1, such that if these two are combined, you will get identity. So here the law of combination being addition and the identity element being 0, what is the inverse of an integer? It is simply the negative of that. If X is added to minus X, the result is 0. So every integer has its negative value as the inverse number. So that when you combine these two, you get the identity element, which is 0 in this case. By associative property, we mean if you combine the integers, say a plus b plus c plus d, like this, you can associate any two of the collection in any way you like without usually changing the order. So you can add d and c first, then add it to b and then to a, or you can write a plus b plus c plus d. You can add c with b and add the result of that to d and the result of all these to a, or you can also do a plus b plus c plus d. You can add the integers by adding a and b to get a result and doing the other additions as indicated here. So binary combinations in a collection of the elements can be associated in any way you like, provided the order in which they are written in the summation is not changed. In the case of integers, even if the order is changed, there is no harm. But in the case of symmetry operations, the order in which symmetry operations are written are associated without changing the pattern in which these are written. The same example of integers, positive and negative, excluding 0, can form another group where the law of combination can be multiplication, real products. And in that case, the identity element will be 1. You can multiply any number with 1, leaving it unchanged. You analyze the other properties for that abstract group. Now coming to our symmetry operations, here the binary combination is simply one operation followed by another operation done on the molecule. And if you combine one operation with another operation, the result will be one or another operation already present in the set. Consider all the operations we have written for water molecule. Identity has to be included, then only the group property will be satisfied. Then we have C2Z, then sigma V X Z, sigma V dash Y Z. With the Cartesian coordinate system, the symmetry operations or symmetry elements can be indicated by the Cartesian notations as well. That helps you to get the product easily. You can multiply or combine any two of these in any way you like, and the result will be one or another among these 4 operations. If a group has got a total of H distinct operations, complete list has H operation, the total binary products will be as many as H squared. Here we have considered the squares of the operations, and also if A and B are 2 operations, we have considered the product AB as well as BA. Sometimes AB will be equal to BA. Sometimes they may not be the same. If 2 operations A and B combine and the result is the same as B and A, then we say that the operations are commuting each other. This is called a commutative property. If the order in which the product is taken is immaterial, we call the binary combination as commutative. The possible binary products here will be 4 squared, which is 16. And all the 16 products can be written down in the form of a table, which is called group multiplication table. Multiplication table. Group multiplication table. It contains H rows and H columns, where H is the total number of operations. So there will be 4 columns and 4 rows in the multiplication table for the water molecule. Every column and row will be headed by the group operations. The multiplication table frame will look like 1, 2, 3, 4 columns headed by identity C2Z, sigma V X Z, sigma V dash Y Z, and 4 rows 1, 2, 3, 4. Every row is also headed by identity C2Z, sigma V X Z, sigma V dash Y Z. So this is the frame of the multiplication table, it contains as many as 16 boxes, and you have to fill in each box with the product of column operation followed by row operation. Each box filled in as column element followed by row element. Column element followed by row element. This is the column element, this is the row element. So if these two are combined, the result is identity itself. Because identity is an operation that combines with any other operation, leaving it unchanged. So writing the first row is very, very easy, because C2Z into identity is C2Z, it is unchanged. Sigma Vxz into identity will be sigma Vxz. Sigma V dash Yz multiplied by identity will be sigma V dash Yz. In the multiplication table, the first row is quickly written. So also the first column can be quickly written, because it all involves multiplication of identity with all these, and all these will be left unchanged. So this with this gives C2Z, this will be sigma V xz, and this will be sigma V dash yz. Then what will you write here? It is column element followed by row element. It is C2 squared. We know Cn to the power n is identity. So C2 squared will be identity, and sigma V xz, sigma V xz. Any sigma squared will be identity. Therefore, these two will also give identity. Sigma V dash multiplied by sigma V dash, that also gives identity. So fill in the boxes with the result which are easily obtained first, and then you worry about others. What about this result? It is sigma V xz, sigma V xz followed by C2z, and we know how to get this product. Imagine a general point x, y, z. First you do the sigma V x z. X and z will not change. Y changes to minus y. Then you carry out C2z. Rotation about the z axis 180 degree will change only the coordinates other than what is implied in the notation. So z will not change, and x will change to minus x, and minus y will change to plus y. Now what is a single operation that can convert xyz to minus x, yz? It is evidently sigma v dash yz, because y and z is not changing. X is converted to minus x, sigma v dash yz. So we will write here sigma v dash yz. In this manner, you can fill in all the remaining boxes. There is a simple theorem which can help you in completing the multiplication table, because when the table is fully written, you will realize that every row and every column is simply a rearranged list of the same operations. When every row and every column is analyzed, you will realize that none of these will contain a symmetry operation more than one time. Every row and column will contain a particular symmetry operation only once. Here all the four are here. Here sigma v x z is there, sigma v dash y z is there, identity is there. So the only missing in this column will be C2Z. So even without working it out, you can complete that. The rows and columns in the multiplication table is just a rearranged list of symmetry operations. This statement is often called rearrangement theorem pertaining to multiplication table, and it helps you to complete the table even without solving all the binary products. For example, what will you write here? Already 3 have come, C2Z, identity, sigma v dash. So naturally it has to be sigma v x z. And having these three, this box should be containing the missing one, C2Z. And having these three, only missing one is sigma v dash y z. And here C2Z is there, identity is there, sigma v dash y z is there. What is missing is sigma v x z. So the multiplication table has been completed. In a similar style, we can work out the multiplication table for ammonia molecule, which has as many as 6 operations. Ammonia has got identity C3, C3 generates another distinct operation C3 squared. All the distinct operations, the complete list has to be written while you discuss the group properties of a particular molecule. Then we have sigma v dash and sigma v2 dash. Cartesian coordinate system is not helpful in getting binary products, and I have demonstrated how a particular product is obtained. For example, how do you get, say, sigma v dash multiplied by sigma v2 dash? Suppose I want to get this product. You write ammonia molecule in this way, H1, H2, H3. This is sigma v, this is sigma v dash, and this is sigma v2 dash. So first you do the sigma v dash. On reflection of here, 3 and 2 will change. H1 remains there, 3 and 2 will change, 2 will come here, and H3 will come here. Then to the sigma v2 dash, this is the sigma v2 dash, so this is the sigma v2 dash. These two get interchanged, and you get H2 here, H1 here, this H3 remains H3. So these two operations have been done. Now analyze the starting molecule thoroughly and compare with the end look of the molecule, which a single operation can convert this one to this. It is one among these. This is H1, now the position of H1 is here, as if you have rotated it by 120 plus 120. This is H2, but that H2 has come to this side, again 120. S3 has come to this side. So every hydrogen atom in the final look of the molecule has been turned by as many as 120 into 2, that is 240 degree. And 240 degree rotation involves two 120 degree rotations, to which we have been calling the notation C3 squared. So we got this result as C3 squared. The multiplication table will be having 6 squared or 36 boxes. You take it as an exercise, as an home assignment, to work out the multiplication table of ammonia molecule. Give 6 columns with these as the headings and 6 rows, again these as the headings of the row, and within the box fill in all the possible products. Then ultimately, towards the end of the filling of the table, you can employ the rearrangement theorem. Whatever operation is missing in a box, you simply include that. In that way, the complete table can be written. Because it is time consuming, I am avoiding that. Now what is the second property? Identity. Identity, the act of doing nothing, the operation of no operation is to be included. Then only the symmetry operations can be qualified as a mathematical group. Thirdly, any operation X will have an inverse such that when the two operations are combined, you will get identity. The combination can be either way, X inverse, the inverse can combine with it in a commutative style. The ultimate result will be identity. And what is the inverse of this operation? You get, our list was identity C2Z, sigma V X Z and sigma V dash Y Z. You get identity by combining C2 with C2. C2 squared is identity. Sigma V X Z with sigma V X Z itself. Sigma V squared is identity. Sigma V dash squared is identity. So what is the inverse of each operation? The inverse of each operation is that operation itself. Because when you take the square of this, you are getting identity. Then identity property is there. Inverse property has been written. The last one is associative property. Suppose I take the product C2 sigma V dash. I can combine these two and the result can be combined with C2 or C2 sigma V dash. I can combine these two. The ultimate result will be the same. You can easily check it with the multiplication table. What is sigma V dash sigma V? The product of these two is actually C2 and C2 followed by C2 will be identity. Then when these two are combined, you will get sigma V dash from the multiplication table. I remember the multiplication table. That is why I wrote the product as sigma V dash. Then again sigma V dash, you get identity. The ultimate result is the same, provided any two operations are associated initially without usually changing the order in which these are written. In the case of water molecule, the product of any two operations AB is the same as the product of this operation written in a reverse manner. AB will be equal to BA. Such molecules where the binary combinations of operations are always commutative, you call these groups as abelian group. Abelian group. What is an abelian group? A group where the combination of symmetry operations is commutative. One more point, molecular groups of the symmetry operations are called point groups. We use the word point group. What is the importance of specifying this word point? It only says that when any operations on the molecule are done, at least one point remains unshifted. At least. If the identity is done, none of the points are shifted. But in the case of water molecule, if you do the C2 axis, C2 rotation or sigma V dash, the point at which oxygen is sitting is not shifted. It only just gets rotated about its own location. So there will be a central point in any molecule through which all the symmetry operations will pass, and that point will be unshifted. This is specified because the symmetry operations and the symmetry groups are also employed in describing the lattice-based crystal structures, and there are some new operations in the lattice-based crystal structures where the whole molecule is moved from its original position to another position. Such a movement is called a translation. There are operations like glide plane, screw axis where translational motion is involved. So all the points in the molecule during the translation will be getting shifted. Therefore, the crystallographic groups are called not as point groups but as space groups. But molecular symmetry groups are called point groups. With this, we are concluding this particular video talk. Thank you.